Greetings and welcome to another video. So in the last video, I spent a lot of time looking at this, and it's sort of been a 2 steps forward, 1 step back thing. What you have here is something that vaguely resembles Thane-Hines bitoroidal transformer, but whereas he uses different material with a different magnetic permeability for the secondaries, I'm just using an air-gapped E-core. And just to go over this for, maybe like the 10th time here, but it's when you pulse your primary, and then when you pull off power from the secondary, if the magnetic flux has 2 paths to go on, the detrimental lens path going back to the primary can be mitigated, or perhaps with different materials nearly eliminated, but in this case mitigated, and instead it flows on the alternate path along the outside here, and that path is actually beneficial. So as we saw in the last video, when you load one of your secondaries, you get more power out from the other secondary. And that's because some of that back EMF, which would normally be flowing back to your primary, flows around to your secondary. So as I said, this is 70 milliamp draw, 250 milliamp hours. So this will take 2.5 hours or so. So I'll just talk at you for like 2.5 hours, and then we'll get back to I'm joking. All right. So I think we said we got to go down to 28 volts. We're down to 33.3. So I don't think I can talk the whole time. I'll shut up now, and I'll come back when I have the test bed set up. So run it at 36 volts, and then have 18 volts on one side, 18 volts on the other, and charge those. So 4 batteries that you're running it off, 4 batteries that you're charging, and see what happens. So here's the setup about ready to go. Yeah, I'm not going to use these batteries, but I was just putting the batteries on there to see how things behave. So here it was running it at 27 volts. That's milliwatts in and out, and did finally get past 2 again. But at the same time, it's 14 milliamps hours, milliamps and milliamps. The 9 volts, I think they're like 200 milliamp hours. So in other words, it's still going to take like 5-10 hours to see what's going on, but it's not going to take like a week or two with 5 amp hour lead acid batteries. So I'm going to have something to eat, and then I'll fire this up and show you it working, and then I'm going to keep track at the half hour and the hour until I get bored. One other thing I'd say before that, I wanted to run it at 36 volts. This Comus AC37 is a 60 volt AC switch, so you can get 30 positive, 30 negative. I'm sorry, 9, 18, 27, 36. I wanted to run it at 36 volts, but if you're going from 36 and it swings to, say, negative 30, which would be about where it is, then that's 66 volts, and you're either going to blow the switch up or it's just going to be bleeding current across it, which would be bad. So these little white ones that I'm using there are 100 volt AC switches, so you could go up to 50 volts. The problem, I gave it a try. The problem is they're slower switches and they have a bit more internal resistance. So while this number, while still above 1, would have been like 1.4 or something like that. So I'm going to need to spend some time on DigiKey if this works, finding something that's a 100 or 200 volt switch that switches fairly fast and has low on-state resistance. So back at you in a moment. Just a couple other things before I fire it up. So what I'll do is I'll put 3 in series for 27, and then I'll take 4 batteries, 2 on each side in parallel. So 27 going down to 9. I would have liked to have gone 36 to 18, because you can't be exactly sure, what sort of load it is. But what I did was ran it at 27 volts into the caps to here, and I saw how much it bounced back, and it bounced back a little bit less. So we're in the same ballpark as if you had a 1000 ohm load, which is what I had with this. So I think it's between 100 ohm and a 1000 ohm load, so it might be a little bit worse than that, but it's in the ballpark. So this is a bit of a kind of spaghetti mess here, but it's what we got. So we got two 9 volts in parallel here coming off of this cap, and we got two 9 volts in parallel here coming off of this cap. It's the meter on there, and that's the meter on there. I discharged those batteries till they were completely dead, and they've rebounded back to there, and I charged these batteries, and that's what they're sitting at there. So first thing I'm going to do is just run it a few times through the for loop. What I'm worried about is whether all of the connections, sometimes these alligator clips actually are discontinuous and you don't know it. So I'm just going to run it, and what we should see is this go down a little and these go up a little, and then if that works, then get rid of the for loop part and just let it run, and then check it in 5 minutes and 15 minutes, half hour, an hour, 2 hours, so on and so forth. Okay, so this is good. So we've got it running off of the batteries now. When you hear it buzzing, see the primary is going down, and that secondary is going up, and that secondary is going up. What I'm going to do is I just want to check and make sure this thing is rebounding the way it should, and then I'll run it continuous. Okay, I did diddle with the timing a little bit, but we can see it's gone from 27 back to about 19 and a half, so good enough to run it. Okay, so the final thing will be to get rid of the for loop. These batteries are charging really damn quickly, much faster than I might have ever guessed. So now we just compile it and let it run. It's 8:04. We'll check back on it in 5 minutes. So this is where things stand after 5 minutes. So what I'm going to do is let it rest for 5 minutes and see where everything's at. So after 5 minutes rest, this has gone from 27.99 to 27.06. This is up at 8.89. And the other is at 8.90. But I got that backwards. So this went down a little bit under a volt, and those two went up about 0.7, and that should be 8.89. So over the first 5 minutes, that went from 29 to there, for a drop of 0.93. You have two on each side, so if we put them in series, that'd be 16.52, and that would be 17.8. Again, there's two of them, so 16.48. So we gained 1.28 on one side, 1.3 on the other. So we're up 2.58, and we're down 0.93, but it's too early to tell anything yet. So let's run it for 15 minutes. All right, coming up on 15 minutes. It's the run batteries, the charge batteries. The one thing that bothers me is that these things are supposed to be fully charged at like 9.3. So either they're charging incredibly fast, or more likely that those curves that I've looked at for how these things charge don't apply to a pulse charge. And what I really hope is that the pulse charge isn't effing with the batteries. But let's give it 5-minute rest and see what things look like. So that's what we got after 15 minutes and letting it rest 5 minutes. The thing I don't get is, I thought that's like fully charged with these type batteries. And 26.39, I mean, I thought they're like 8.4 volt batteries, so that's right down into the working range. I don't know what's going on. What it looks like is these are charging faster than I would have thought, and this is going down faster than I would have thought. But I'm going to run it for a half hour now. I'm just going to let it run for an hour. It's been about 40 minutes. We're down to 25.2, and the way these things go is it holds steady for a while, and then when it's near discharge, it just drops off the face of a cliff, which I think, I don't know, maybe at 24 or 25, somewhere around there. I mean, I didn't think these things could charge this high, so I don't know if this is because of pulse charging and whatnot. So in essence, I don't really know what's going on, but it looks like it works. Yeah, this thing's still holding up really well. I don't know how high these things are supposed to be able to go. If it weren't pulse charging, I think that would be too high. And again, I hope the pulse charging isn't screwing up the batteries. Well, this is actually getting a bit exciting because it seems to be confirming what I was seeing on the spreadsheet. Let's just, I think we're at like 45 or 50 minutes now. So one thing, this thing's starting to just hold more like a rock. I think it was at like 0.21, 25.21, maybe like a half hour ago. These were at, I want to say it was like 9.4 something. Now they're at that, 9.55 on that one, and 9.50 on that. One of the issues here is, you know, I don't know if this is good or bad. I don't know if I'm like just overcharging the batteries and destroying them now, or if these things are supposed to go up to, you know, like 10 or even 11 volts when you have a full charge. But this thing is finally starting to discharge slowly. And so when it started off 27.99, we're at 25.18. This is with it running. So what is that? 28 to 25 would be 3. So 2.82 volts down. It's at 9.55. It's at 8.26. I was coming up on 9. It was doing 9.56. So 9.56, 8.26, 1.3. There's 2 there, so that's 2.6 volts. 9.5. Oh, let's just pretend that it's 2.6 and 2.6. That'd be 5.2 volts, and this down less than 3. So it's sort of like, you know, close to like 2.0, right around what we were calculating. But it's all confusing because you got the charges and the discharge curve, and you're not going to find a charge or a discharge curve that I can think of for pulse charging nickel metal hydride. So I don't know if this is good or bad for them, and whether it was charged after 5 minutes or it needs to go another 2 hours to be fully charged. But this thing's finally looking like it's got its giddy up on it. It's going to just try and hold this voltage for a long time. Really, the other thing that'll need to be tested on this, I won't put it in this video, but I'll try to remember to mention it in the next one, is just to make sure that just because these things are getting voltage, that it's not some sort of like weird surface charge or something. I don't think it will be, but you know, the thing to do after this is not just to flip them out to there and see what it does charging those. The first thing to do is just to put a resistive load on there, and to make sure if you put, you know, like a 1K ohm load across here, it doesn't just go, which I've seen stuff like that before, which I'm hoping that this is not doing. But if it's not doing that, that it's going right in accordance with what we saw, you know, calculating things on the spreadsheet in terms of COP. Okay, this is actually kind of getting interesting, at least to me. I think last time I mentioned it was at like 25, or I'm sorry, like 9.55 or whatever. Shut it down. I've been running it for another half hour. That's where that's at. And this is at about the same thing. The reason that's interesting is the charge curve for these under, you know, I don't know, constant voltage or constant current, whatever it is. You know, they take off, they sit there, and then they do a last boom, and then it kind of even goes down a little bit, and then it's done. So it's not getting any further charge acceptance. It's just sitting there right at 9.52. Well, now it seems to be going up a little bit, but this has been here for 15 minutes without this or this budging. So I think they're done. I think they are. I think they're done, and this thing's going down. So what I'm going to do is I'm going to take these out, and I'm going to rest them overnight. And then, as I said, put a load on it and actually make sure that it has, you know, however many milliamp hours of capacitance. Since this thing is still holding, though, I've got a couple. These things are like 10 years old. I'm going to throw them on there, and they're kind of garbage, but I don't know what the pulse charging will do with them. And as long as this thing's going, I'm gonna keep charging batteries. I got 2 more of these. I got one of these that's dead, and I've got another one of these. But we'll start with these, and we'll see if this thing's still going. I don't know whether to keep this going or not. I think we were at 9.55. I think it's hit a wall, and that's what it shows on the charge curve for these. So I think I've been done here since this thing was at like 25.16. I'll run this down to 25.1, and then I'm going to say they're done. Yeah, I went back and looked at the video. This thing was at 9.55 before I shut it down for a rest. It's having trouble even getting back to that, and this is what you would expect from the charge curve. So I think these things have been done for a half hour, and I'm just draining these batteries out. So that's not good. So now, you know, again, I'll have to do the test tomorrow, which is to put resistance across here. But what I'm going to do is take these out and let them set for a day. I can't remember whether these things start at 27.99, so 9.33. I might have pulled them right off of the charger, or they settled overnight. I can't remember. But either way, if these things settle above 9, that should be fully charged if they don't collapse like a rubber band when I put a bit of resistance across them. But I'm going to say that that's not going to happen. So what I'm going to do is use these crappy 10-year-old ones, as long as this thing's still throwing out current. Let's see if we can charge these. And then if these charge up, and they're up at 9.4, 9.5, I got 2 more. And we'll just keep going with these 3. So again, I won't really know until I load those batteries that were charged to make sure that they can handle a load. But it sure seems to be working. And I've just thrown some random, these things are ancient, and so they're probably crappy. One's at 8.4, one's at 7.37. As long as this thing's still churning out the spikes, let's fire her up. Okay, one of them's toast. The other one seems to be doing all right. Let's get rid of that one and see if we can put in a different one. Okay, here's like a 2-year-old Tenergy from when this thing went dead. So it's at 8.22. And there we go. And we're off to the races. And how's this guy? Not too shabby. Rebounded before we were at like 25.1, and it's not like, this is not bad. Okay, this is really starting to get fun. So here's another battery. It was dead, whatever. It's up to 9.42. Now I think we can say between 9.5, 9.55, it's fully charged. There's this one, which is 10 years old, but was fairly good. It's up to 9.8, which I don't, I think it's because it's an old battery. I don't know if pulse charging rejuvenates it or like just destroys it quicker. But I'm just going to leave it on there as ballast and see if we can get this one up to 9.5, 9.55, because this is a good battery. And we're at 24.98 now. So I don't want to be, like famous last words or whatever, because I need to put a resistive load on the ones that were charged. But I thought I would mention this. That is that the way I was measuring COP previously with the resistors I'm saying may with quotes, greatly underestimated the actual COP. The reason for that, and I thought about this in the last video when I shortened and tidied up the timing, like how long the switch is off for, how long you're charging the thing. There's a little more tidying you could do. But, a 100 ohm load was way worse than a 1K ohm load. When you tidied the timing up, the 100 ohm improved, the 1K ohm improved, but it didn't improve as much as the 100 ohm. So what I'm saying, how do I explain this? You're taking this cap, you charge it up, the cap discharges into here, you gather off the secondaries. Now let's just suppose you had a short across each of the secondaries and you put a meter on there. Now while the meter's on there, this cap, the first thing is the switch has to shut off, which takes like half as much time as you use charging, or 2/3 of the time. The cap has to charge back up. That switch shuts off. Like 3/4 of the time, you're just doing book work, and 1/4 of the time you're actually discharging the thing. For that 3/4 of the time, if you had a short, this thing would discharge to 0, and you say, well, nothing happened. And so that's why with the 100 ohm it looks so much worse, but I don't think it is all that much worse. And with the 1K ohm, it's like, oh my gosh, now we're up to, really, I saw a COP of 3, but COP at 2.2 instead of a COP of like 1.8. So what I'm saying is, and not to be overly dramatic, but the COP could be twice or 4 times, depending on how you're measuring it with what cap. I'm sorry, with what resistor, than what was being seen, what was being calculated before. If I really had to guess, I think it's probably like twice as good. And this is starting to maybe make a case for that. I mean, we're getting out to like 6 batteries charged. If I'm right that the other 4 batteries were fully charged and I just kept hitting them, that's a waste. What I'm saying, this thing's still going. We're coming up on 6 batteries charged. I'm running out of batteries. I got one more of these. I don't know if it's a piece of garbage. And then I'm going to try and charge non-rechargeables and just keep going until these give up the ghost. So you see, as far as I can tell, this thing is just about charged. I'll give it a little while. Maybe we can get out to 5.2, but I think that's charged. All right, well, I mean, if this is right, we got another fully charged good battery. This one is an old battery, but I think it's fully charged as well. And I can't wait till tomorrow. I'm going to put a load on this and we're going to find out. So after about an hour or so. This is settling at 9.22. Again, I can't remember whether I pulled those right off the charger or whether they had settled for a day. But we're at 9.22, and what I'm going to do is put a 470 ohm load across here. So let's say 10 volts, 500 ohms, 10 volts, 5 ohms, 2 amps, 100, 200 amps, 20 milliamp. That'll be a 20 milliamp load, like right in the ballpark of what you would want something like this to handle. So well, let me, I'll show you on the telestrator. What a stupid fucking name. So the discharge curve for a nickel metal hydride goes zoop, man, zoop. And so when I put the load on, I expect it to go zoop. But what we want to see is that. What we don't want to see is 5 minutes in, the thing's at 7 or 8 volts. And if so, then it's all been in vain. The fellowship has failed. Not if we hold true to one another. Let's earn some work. Let's see what happens. So this is really the whole thing of whether this has worked or not, which so far has been, right in line with what you would expect from what we're seeing on the spreadsheet. But let's see what the hell this battery does. Oh, this is beautiful. This is just the steep down curve part. And, it's going down. It's not collapsing, though. It's not a surface charge. Once this thing gets down to like 8.6 or 8.4, with that load, it'll sit there for hours and hours. I can tell that right now, because it didn't just collapse on the down part there. Oh, this is wonderful. This is wonderful. So we've charged 6 batteries from dead to full with 3, and these have still got plenty in them. Here's one more. I don't know if it's a piece of crap or not. And then I have to go to, these are dead. Maybe we can recharge non-rechargeables with pulse charging and see what happens until this starts to go off the cliff at the end, and then I'll stop before I damage the batteries. All right, well, these are still charging. I mean, here's a really dead ancient nickel metal hydride. Here's a dead alkaline. Let's see what happens now. All right. Is that the wrong one? Let's try that again. There's the alkaline going. This nickel metal hydride is, I think it's toast, but I'll just let it go anyways as ballast. Be interesting if the alkalines are rechargeable. Probably not more than 10-20 times. I'll let one on. I think that nickel metal hydride's toast. I'm going to put in another alkaline. Okay, I think this is a good place to wrap the video up. This is starting to get near where it's going to go off the cliff. It's not there yet. We had 3 batteries. We charged 6. I left some of them on for too long. Yeah, it's starting to go off the cliff. Now I'm charging non-rechargeable alkalines and trying to get something out of them. So it is in accordance with what I was seeing on the spreadsheet, and it's actually better. And I talked a little bit earlier in the video about why I thought it might be better, and it looks like that's true as well. So in the next video, what we're going to do is we're going to improve this. And there are like 2 obvious things that can be done. Aside from worrying about the air gap and everything else, there's just 2 obvious things. I'll talk about that in the next video and see how it goes. And the other thing is to pick up a reasonable solid state that can take us up to 50 volts instead of the 27 that we're running at now. So this is starting to go down pretty quick. I'll end it here. Live long and prosper, and talk to you soon. Bye.